Okay, so the last type of shape we have for volume is semicircles. So I just kind of pasted a picture of here. So we've got some graph. This will be the equation. We'll graph it here. And then what we're doing is we're stacking up a bunch of semicircles like that are lying perpendicular. So it's creating like a 3D figure. Think about if you were to like put a tint over this, it creates that 3D shape. That's what we're finding the volume of. So with semicircles, what's going to go in our integral is the area of a semicircle. And remember, area of a semicircle is just half a circle. So we're just going to do half the area of the circle, which is pi r squared. So if I look at this picture here, okay, the radius is just measured from the center of the circle to the edge. So from here to here. Okay, so my radius this time isn't the length all the way up to the top of my graph. It's just going to be half of it. So we'll kind of, when we work through the first example, we'll talk about how to set up the length for the radius. So to find the volume of this one with the semicircular slices, we've got y equals x squared. So just like all the rest of them, that's going to be the first thing that we graph. So when I plug in, I'm going to plug in 0 and I'm going to plug in 2, and since it's x squared, that'll be a parabola. So I'm just going to connect those 2 points with a parabola. So 0 squared will be 0. Then when I plug in 2, 2 squared is going to be 4. And then I'm just going to draw my parabola and then close it off at the x-axis. Okay. Then I'm going to draw just one of my semicircle slices. Let me try to make that a little better. And again, I just draw it somewhere in the middle. So there's the bottom of the semicircle. So if I look at the radius of this, that's going to be from here down to the x-axis. So this length right here represents the radius of the semicircle, okay, which when we did the squares in the isosceles triangle, the side of the square or the base of the isosceles triangle went from the x-axis all the way up to the graph that we drew. Well, now since it's a semicircle, the radius is only half that length. So anytime you're doing volume by slices with a semicircle, your radius is always just going to be half of whatever your equation is. So the radius is just going to be 1/2 times x squared, which is just 1/2 x squared. Okay. So then before I set up my integral, I'm going to look at my area formula, which is 1/2 pi r squared for semicircles, always half of a circle. Okay. I'm going to plug in the radius, okay, which is just half of the given equation. So for semicircle, so it's 1/2 x squared squared. Okay. So the radius on the semicircle problems is always going to be half of the equation. And then we're going to simplify just like we did in all the other ones. So this is going to be 1/2 pi. I've got to square the 1/2, which is 1/4. And then x squared squared is going to be x to the 4th. And then I can just multiply the two coefficients, the 1/2 and the 1/4. And that's going to give me 1/8 pi x to the 4th. Okay. Now we're ready to set up our integral. Okay, and so remember, this is always our a value. 2, the second number is always going to be our b value. So when I set up my integral, I'm going to go from 0 to 2. Okay. My area was 1/2 pi x to the 4th, and then this dx just means I need to do the antiderivative. So now I'm going to do the antiderivative. So my x, the new exponent is going to be 5. So the coefficient is going to be 1/5, but then I have to multiply it by the 1/8 pi that's already there. And so this 1/8 times 1/5 is going to be 1 over 40 pi x to the 5th. And then I can plug in 2, I can plug in 0, and evaluate that. Okay. So when I plug in 2, that's going to be 1 over 40 pi times 2 to the 5th. And then I'm going to get that number and I'm going to subtract what I get when I plug in 0. And again, when I plug in 0, 0 to the 5th is 0 times 1 over 40 pi, still 0. So I don't really need to worry about plugging in that 0. My answer is going to be whatever I get when I plug in 2. So 2 to the 5th is going to be 32. Okay, so this is like 32 over 1 times 1 over 40, which is 32 over 40 pi, which is going to be not 8. I'm going to reduce this. I'm going to divide them both by 8, or you can just divide by 2 until you can't divide by 2 anymore. But if I divide both by 8, that's going to give me 4 over 5 pi units cubed. So let's go ahead and do one more of these. Okay, so now we've got y equals 4 times the square root of x. And we're going to graph that from 0 to 4. So if I plug in 0, square root of 0 is 0, times 4, still 0. If I plug in 4, square root of 4 is 2, times 4 is 8. Okay, so I'm counting by 2's over here. And then I'm going to go ahead and graph the square root curve, close it off. And then I'm going to draw one of my semicircle slices. So there's the base of the semicircle. And then my radius. Let's see. Is going to be from the center of the semicircle down to the bottom. So my radius is going to be half of the equation. So the radius for semicircles is always half of your equation. So half of 4 times the square root of x is 2 times the square root of x. Okay. Then I'm going to simplify my area formula. So area of a semicircle, half the area of a circle. So that's going to be 1/2 pi. I just found my radius over here to be 2 times the square root of x. So that's going to be 2 root x squared. And then I'm just going to simplify. So this will be 1/2 pi times 2 squared is 4, square root of x squared is just going to be x. And then I'm going to multiply the 1/2 times the 4 to get 2 pi x. And that's what's going to go into my integral when I set up my integral, which will be the next step. So then I've got the integral from 0 to 4 of 2 pi x dx. Then I'm ready to do the antiderivative. So my x is going to become x squared, so the new coefficient will be 1/2, and then I've got to multiply it by the 2 pi that's already in front of it. So 2 times 1/2 is just going to be 1. So this is just going to work out to be pi times x squared. And then I'm going to plug in 4 and plug in 0. But when I plug in 0, again, I'm just going to get 0. So I really just need to look at what happens when I plug in 4. So that's going to be pi times 4 squared. So 4 squared is 16. So this will just simplify to be 16 pi units cubed. And we're always going to leave our answer for semicircles in terms of pi. So that's the last example we have for semicircles. So just on the next slide, I want to kind of recap what to use for what type of shape. Okay, so when you're doing volume by slices, if you're using squares, Okay, your area formula is area equals side squared, and what you're going to use for the side is whatever the y equals equation is. So if it's y equals x squared, you use x squared for the side. If it's y equals 2x plus 1, you use 2x plus 1 for the side. That's what you'll plug in for your s right here. If it's isosceles triangles, your area formula is 1/2 base times height. And since it's isosceles, the base and the height are always going to be the same. Okay. And again, just like with the square, you're going to use whatever the y equals equation is for your base and your height. Okay, so if it's y equals the square root of x, that's what you use for both the base and the height. Okay, now if it's a semicircle, this is an extra little 2 right here. Your area formula is 1/2 pi r squared. And your radius is going to be different. Okay, whatever the y equals equation is, you're just going to use half of that. So if it was 2x squared, what I would use for my radius is just half of 2x squared, which would be x squared. Okay, and those are the 3 types of shapes we're going to use for volume by slices. So the worksheet you have for today is mostly just examples with semicircles. I think there's about 3 of them, and then there's an example with a square and isosceles triangle just to refresh your memory on those 2.